The application of biomaterials in a human implant. A biomaterial is any materials, natural or man-made, that replace a damaged a living part. For example, from the following figure is the dental implant, hip replacement, and the valve. Definition: outline the definition, characteristic of biomaterials, history, biomaterial science, generation of biomaterials, example of biomaterials, details of axial cavity, details on hip replacement, biocompatibility, challenges, and the biomaterials as emerging industry. Definition: a biomaterials are non-variable materials used in medical devices intended to interact with the biological system, defined by their application, not chemical make-up. The characteristic of biomaterial: first, the physical requirement, hard material, flexible materials. Chemical requirement: must not react with any tissue in the body, must be not toxic to the body, long-term replacement, must be not be biodegradable. The history: more than 2,000 years ago, Romans, chains, and Aztec used gold in dentistry. Turn of century of the scientific implant became available. 1973, polymethyl PMM as a type of the polymer used introduced in the dentistry. 1985, purple suggests decolled fabricated can be used to fabricate an artificial prosthetic. 1916, currently used PMM, ultra molecular weight polymer, and stainless steel for total hip replacement. Later 1916 to earlier 1917, biomaterials field solidified. 1975, Society for Biomaterials formed. The type of the material here is the biomaterial polymers, which is used in a scan synthesis, ocular implant, drug delivery device, ceramic, used in the bone replacement, heart valve, dental implant. The semiconductor material used in the biosensors, implant microslodes, and materials which is used in the orthopedic secure fixation dental implant. Biomaterial since biomaterial cover all the classes of the material, which include the metals, ceramic, and silicon. This diagram shows the some example where certain type of material can be used, for example, in the valve of the heart, in the implant here, in the dental implant, and the others. First generation of biomaterials specified by the physician using come and pose material. Most successes were assigned rather than any designed. Second generation of biomaterial developed through cooperation of the physician and engineers. Engineered implant using coming and pose materials. Built on first generation experience, use advanced in material science form of the other fields. The third generation of the implant, bioengineering implanting using bioengineering materials. A few examples on the market: semi-modified and new polymeristic device, many under development. Example of biomaterials application: heart valve, artificial tissue, dental implant, intraocular lenses, vascularized graft, and hip replacement. Heart valve, fabricated from carbon material, elastomers fabricates and natural valves, must not be react with chemicals in the body. Attached by the polyester mesh, tissue growth facilitated by the polar oxygen contained groups. Heart valve almost as soon as valve implant. Cardiac function is restored to near normal. Perfected tentling disc heart valve using the most readily. Perfect heart valve is the following figure represents the application of the heart valve or artificial heart valve in the human. Artificial tissue, biodegradable polymer result of the condensation of the lactic acidic and nucleic acidic. Dental implant, small titanium fixation that serves as the replacement of the root portion of the missing natural tooth. Implant is placed in the bone of the upper or lower jaw and allowed to bond with the bone. Most dental implants are pure titanium and the screw shaped cylindrically. Capability of the bonding to bone, a phenomenon known as the osseointegration. Bioinert, there is no action in the tissue and no rejection or electric of the reaction. The following figure represents the part or the group of the tantalum implant. This part represents the titanium alloy, and this the crown is made from the ceramic or polymer. Intercooler lenses made of PMM, or this is the type of the polymer, silicone, elastomer, and other materials. By A75, more than 15% of the population suffers from cataracts. 1.4 million implantation in the United States yearly. Good vision is generation restored almost immediately after the lens is inserted. Implantation often performed on the outpatient of the basis. Vascularized graphite must be flexible, designed with open pore structure, often recognized by the body as foreign. Hip replacement is the one of the important applications for the use of the biomaterial. Most common medical practice using the biomaterials: corrosion resistance, high strength metal alloys, very high molecular weight polymer, thermoplastic plastics. Some hip replacement ambulatory function is restored within days after surgery. Others require an extensive healing period for attachment between bone and the implant. Most cases, good function is restored. After 10 to 14 years, implant losing required another operation. Hip replacement. The following figure represents the part of the hip replacement. Vascular graft. Achieve and maintain homeostatic, porous, permeability, good structure retention, high fatigue resistance, low thrombodynamic, good handling properties, and biostability. Brady's, Weaver, and kinetics: porosity, permeability, thickness, pore strength, kink resistance, short resistance, wall thickness, tensile properties, and level resistance. Kinetic graphite, and the following represent the kinetic graphite. Biometers are the example, the biochemistry of the artificial joint. The following figure represents the normal vacancies of the orthopedic hip. The following figure, normal hip, note the space between the femur and the actuator due to the cartilages. Orthotic hip, no space visible in the joint as the cartilages is missing in this part. To design issue in attaching material to the bone. The geometric and material design of the artificial surface, design of the interface between the artificial joint and the soliding point. Two attachment method. The first attachment using the polymetallic polymer PMMA cement to adhere to the material to the bone. The another figure using the pores, in this part the pores, metal surface to create it upon in a growth interface. The compression modulus of the elasticity, this is the figure, represent the value of the Young modulus for the different material or the biomaterial, and the steel seal which have the maximum value for the Young modulus compared with the other sponge material. Implant pointing. A pointing interface in the left figure. A pointing interface is characteristic of cemented prosthetic assets, and in the right figure, no pointing interface is characteristic of the non-cemented fit prostheses. Declaration of a problem. Example of a fracture artificial cartilage from a failed hip replacement. Biocompatibility. What do you mean by biocompatibility? The ability of the material to elicit and appropriate biological response in the specific application by not producing a toxic ingestion or immunological responses in living tissue. Strongly determined by way of the chemical structure. Host reaction to biomaterial, thermopasis, hemolysis, inflammation, infection and sterilization, carcination and hypersensitive systematic effect. What are some of the challenges? To more closely reflecting complex tissue architecture and arrangement in vitro, to better understand circulation and intercalation modulation of the cell function, to develop novel material and processing techniques that are compatible with the biological interface, to find better structure for the image of the acceptations. Next generation of the medical implants and industrial thermobaric modulators, interface of biotechnological and traditional engineering, significant industrial growth in the next 19 years, potential of a multi-billion-dollar industry,